Hello everyone, and welcome to AISC's Night School, Seismic Design in Steel, Concepts and Examples, presented by Rafael Sabelli of Walter P. Moore. Today is February 5th, 2018, and this is Session 1, Introduction to Effective Seismic Design. My name is Brent Liu. I am with AISC's Continuing Education Group, and I'll be moderating today's presentation. I want to introduce tonight's speaker, Rafael Sabelli. Rafael Sabelli is the Director of Seismic Design at Walter P. Moore Engineers and Consultants. Mr. Sabelli is a recognized authority in seismic design and steel structures. His experience includes design of new structures, retrofit of existing buildings, nonlinear seismic analysis, and the development of new structural systems. He participates in several national committees responsible for building code development, including several committees here at AISC. Mr. Sabelli is the author of this entire course, and as such, he will be presenting all 8 sessions. So with that, I want to say welcome, Rafael, and I'll hand things over to you.
Thank you, Brent. Hello, everyone. So we have 8 sessions on seismic design in steel. As Brent said, we've thought a lot about the course objectives. The main focus of the course is, of course, seismic design, starting with the principles, and then moving on to the application of these principles to important systems, special moment frames and buckling restrained braced frames. So those aren't the only systems that we have, but those are the design methods that we use for those 2 systems help you understand the seismic provisions for all other systems. And so we want to illustrate the seismic design requirements as applied to those systems, and more or less what we'll call a complete design of a structure. Obviously, it's not going to be a thorough design of every element, but we take it from diaphragms to frames to foundations or to base plates. So it does cover many different aspects of the design. For this class, I've identified as additional resources that hopefully you have or could consider getting. The first is the AISC Seismic Design Manual. This is published in conjunction with the seismic provisions. So I'm showing here the 2010 edition, or the edition that went out with the 2010 seismic provisions, and there will be an edition published very soon corresponding to the 2016 seismic provisions. A ductile design of steel structures. This is the 2nd edition of the textbook. Principal author Michel Bruneau, with some participation from me and quite a bit from Professor Chai-Ming Wang. And this covers quite a bit relevant to seismic design, including behavior of steel and going through the behavior and design of different systems. And AISC has a number of facts for steel buildings, and one devoted specifically to seismic design, Earthquakes and Seismic Design by Ron Hamburger. And that's free to members, and I think that's an excellent resource for understanding the principles of seismic design of steel structures. And then at the end of each session, including today's session, I'll identify a few more resources that I drew on in putting the session together, or perhaps you may wish to draw on in understand the items discussed in a little bit greater detail. Of course, you have the AISC Solution Center, which is a free resource that I take advantage of, and I also participate occasionally in answering some questions. Night School email address. As I said, we start with the principles. So this class is divided into 2 parts. First part being concepts, with today's session an introduction, followed by a general treatment of moment frame systems, and then a general treatment of braced frame systems, and then a look at buildings, including diaphragms and also our system of codes that govern building design. The second part of the class is the application of those principles. So we start by introducing the design example and laying out the seismic design, where the frames go, developing the base shear. Then the next session, we analyze the building and obtain design forces for many of our elements, and we also do the design of the diaphragms. Session 7 is the design of the special moment frames, including beam, column, connection, and base plate. And session 8 is design of the brace frames, again, beam, column, sizing of the brace, and a few connections. So it's quite a lot to include in 8 sessions, and each session has quite a lot in it. Hopefully we'll get through it all, and I will be available to answer questions at the end of each session and afterwards. So, session 1, the introduction to effective seismic design. We'll talk about the need for seismic design, why it's an important load consideration. A little bit about structural dynamics, seismic response spectra, system ductility, and steel ductility in particular, and then the different lateral systems that we have in steel. So let's start with the need for seismic design. This is a list of very large earthquakes in history, some of them dating back quite a lot. So all of these are over magnitude 8.6 and greater. The ones highlighted in red have occurred in the U.S., and as you can see, they're all in areas of Alaska, not necessarily heavily populated areas of Alaska, but in Alaska. So California has the reputation as being the center of earthquakes in the U.S., but that's not really the case. Alaska has had these very large earthquakes, and large earthquakes have occurred in the southeast and central U.S. as well. These are extremely large earthquakes here, magnitude, as I said, 8.6 and larger. This earthquake, Valdivia earthquake in Chile, is magnitude 9.5, killed over 2,000 people, not all of them in cities. People died throughout Chile. 3,000 people were injured, and over 2 million homeless. $550 million estimated damage, which is quite a lot. And tsunamis were generated as well, and so the deaths were even more widely distributed. 61 in Hawaii, and quite a bit of damage as well. $500,000 worth of damage on the West Coast, which perhaps isn't that much, but the U.S. West Coast, but it does show the reach of this earthquake. 138 deaths in Japan, and $50 million worth of damage, and 32 estimated dead in the Philippines. So there can be quite a large effect for these very large earthquakes. This is a list of costliest earthquakes, and again, the ones highlighted in red are U.S. earthquakes. And because of the relative wealth of our country, when earthquakes happen here, there's quite a bit of property loss. The Northridge earthquake, which was only a magnitude 6.7, caused $20 billion worth of damage in the Los Angeles region. You can see that magnitude 9 earthquake, the earthquake and tsunami in 2011, $235 billion. So I guess that's two related load conditions that caused that damage, earthquake and tsunami. So Northridge earthquake, again, not an extremely large earthquake, pretty far down the list in terms of magnitude, but quite a bit of damage, and of course there were people killed and injured. So a great effect, not just economic, this earthquake. 20,000 homeless, which affects not only the people homeless, but it affects the city as a whole and the recovery of the entire region. Over 40,000 buildings damaged. Very high maximum acceleration, but the magnitude of the earthquake wasn't that great. The geographical extent that saw large accelerations was fairly limited. So we've talked about large earthquakes, we've talked about large losses, and of course there are large fatalities. Some of these major earthquakes that hit heavily populated areas, the fatalities end up just being estimates because it's impossible to count everybody. The dead have to be dealt with very promptly. So this list doesn't include any U.S. earthquakes. I guess we're fortunate in that regard that the quality of our construction and our luck has been such that we haven't had these major losses. I believe everyone should remember the 2010 Haiti earthquake. Only a magnitude 7. It's not small, but not one of the largest that we've seen. Over 200,000 people killed, and it's hard to know exactly how many, but in that range, 200,000 to 300,000 people. That's quite a lot, and of course, many injured, many people displaced, and it affects the economy of the entire country. Port-au-Prince itself had close to 100,000 houses destroyed, and close to 200,000 houses damaged, and that leaves a lot of people homeless and affects the recovery of the entire country. And this earthquake was felt throughout the region, Florida, Colombia, Venezuela. So none of this seems acceptable. As structural engineers, we have training, we have ability, and we are well positioned to mitigate a lot of this through proper structural design for seismic loads. So we would like to prevent large-scale loss of life. We can't prevent all damage, but we certainly have the ability to drastically reduce the loss of life that an earthquake causes when it hits a heavily populated area. We're going to try to prevent partial collapse or total collapse of structures, make those very, very rare and unlikely, and thus the level of fatality will be much lower. As a byproduct of this, so that's the intent of the code, to protect life. As a byproduct of protecting life, we will be building structures that are stronger and less likely to suffer large economic losses, such as the total loss of the building because it's out of plumb or so badly damaged that it can't be occupied. We may be reducing the repair cost. We may be reducing the loss of use. So the structure, instead of being out of commission for several months, might be habitable the next day. And because we design for seismic design, we design for seismic loads, the region can recover much more quickly. So if 200,000 people are displaced, it takes a long time to find housing for them. If only 5,000 people are displaced, that's still very significant, but it's something that perhaps the region can deal with a lot quicker. So we're going to focus, of course, on structural design. We want to prevent excessive deformation. We want to maintain our lateral resistance. We want to maintain our lateral stability even under large seismic loads. Of course, we want to maintain vertical support. And also worthy of attention of the structural engineer is the evacuation of the building after an earthquake. Many buildings will be severely damaged and people will need to get out. So maintaining the evacuation routes will facilitate with that. There are non-structural things that cause a lot of damage. Architectural elements, mechanical, electrical, plumbing. The building codes ask that we limit falling hazards. When the seismic loads get large enough, there are There are force requirements for the restraint of many of these elements, and also to prevent obstacles to evacuation and to maintain emergency systems that may be required for exiting, such as emergency lighting. The earthquakes produce multi-directional accelerations. That includes vertical motion. Vertical accelerations caused by earthquakes, they can be quite large, but we do have a gravity system already for our structure. So even vertical loads on the order of 1 g, if they're not present simultaneous with our maximum live loads, they may not cause any significant damage at all in our vertical system. So we don't see a lot of damage for typical structures due to vertical accelerations. There are many structures that are highly sensitive to vertical accelerations, large cantilevers, long spans, and the like. And those may need to have a little bit more attention to quantify what the vertical acceleration is and to see what the response is. But for typical structures, the vertical motion is not something we focus on very much. The horizontal motion can cause a lot of damage. Often our lateral systems are, if we aren't aware of a large seismic load, our lateral systems can be fairly modest. So in a lot of construction that was done in San Francisco prior to the Great Earthquake, there was not a robust lateral system. It was a robust vertical system, but the lateral motions caused a lot of shear and overturning that the structures simply weren't designed for, and there was a lot of damage. So the horizontal motions are really what we focus on the most in seismic design. This is, of course, due to loss of lateral support for this frame. Frame bent over, and the building essentially collapsed due to the lateral forces. And this building had an overturning failure. So buildings, for seismic design, we design buildings to resist this horizontal force and the related overturning. We do this through a combination of strategies. We provide adequate strength and stiffness. Stiffness is important because the lateral deflection causes additional overturning moment. That's the P big delta effect. We provide lateral systems that have a large displacement capacity. That means earthquake-induced lateral drift may cause yielding of elements, but for controlled seismic response, we don't want to cause the lateral system to lose its strength. So we don't want instability due to lateral movement. We may have to accommodate a fair amount of lateral movement, but instability would not be conducive to good seismic performance. And then another strategy is energy absorption. So rather than the earthquake energy going entirely into strain energy in very strong elements, or entirely into yield strain energy due to yielding of elements, we might have energy absorption devices or other strategies to take some of that earthquake energy and reduce response in drift or in member forces. All right, we'll talk a little bit now about response spectra. We'll introduce response history and period-dependent response. So it's often useful to idealize our structures as very simple dynamic elements. Often we reduce it all the way to a single degree of freedom element. So we'll start there in this discussion. The ground moves under our building, and we'll idealize our building as a single degree of freedom, element and mass on some sort of cantilever. And we'll have some response of interest. Drift is usually a response of interest, and perhaps shear and moment, and overturning moment in our lateral system would be responses of interest. And we measure we estimate what that response is as a function of that input motion. So far, it's fairly simple. That response, again, could be anything that we think is significant for design. We might use displacement to monitor our displacement and limit it to a code acceptable displacement. We might use shear and overturning to quantify what we need to design different elements for in our lateral system. Now, the response is not a given just because you have the input defined. The response is a combination of that input with the dynamic characteristics of the structure. So here we see a number of different structures. I'm showing them getting taller and taller, and thus their period is getting longer and longer. And there may be increasing response up to a certain point, and maybe at some point the response starts to decrease. And it has to do with the period of the input and the natural period of vibration of the structure, and perhaps other dynamic characteristics of the structure, including damping and nonlinear behavior. So the response, whatever response we have, is an interaction between the ground motion and the dynamic characteristics of our structure. So recognizing that, we can create these spectra, these graphs, that will estimate some form of response as a function of some form of the dynamic characteristic of our structure. And those are the earthquake response spectra, and we'll talk about different ones. So we can take this ground motion record, and it used to be many years ago we only had one ground motion record. So we would take that ground motion record, and we would perform analyses using single degree of freedom oscillators, and then graph those analyses. So each one of these single degree of freedom oscillators has a different response. So we start perhaps with the short period one, and it's got a response up here, and then slightly longer one, and so on. And of course, I'm just showing a handful of oscillators here, but you could have oscillators at very small increments of period and create a spectrum like this. And you could create a spectrum like this with elastic oscillators or with oscillators with some degree of damping. You can do it with hysteretic models as well. Typically, what has been done is creating a spectrum with elastic oscillators with a defined level of damping. And each earthquake gives, excuse me, if you do that for a number of earthquakes, each earthquake gives some sort of spectrum like this. When the period is 0, that's the same acceleration as the ground acceleration. Then at somewhat larger periods, the response may go up, and then at longer periods still, the response starts to go down with period. Each earthquake has different frequency content, and so you can see spikes and valleys, but if you average a number of earthquakes, it becomes much more smooth. So here is a very rough period versus acceleration diagram. This is actually pseudo-acceleration, so it's a constructed acceleration rather than a measured acceleration. You can do the same thing for velocity, in this case pseudo-velocity, and they are related by the period of the structure. And you can do the same for displacement. So you can see with each of these, they have different regions where they are maximized. For short period structures, people often discuss a so-called constant acceleration region, and that's really just the plateau of the acceleration spectrum. At lower periods, the acceleration can be lower for design purposes. The codes, at least for the principal mode of vibration or the fundamental mode of vibration, the code treats it as if it's a constant acceleration from period 0 up to a certain period. And there's the so-called constant velocity region, which is just to the right of that plateau. And then there's the so-called constant displacement region beyond that. So you may hear these terms when we're talking about seismic design, and you can see that they have some meaning, but they're not perfectly correct for all ground motions. Let's talk a little bit about ductility. What we mean by ductility, types of nonlinear behavior, effective stiffness and period, energy dissipation, and damping. So again, we're going from a ground motion to a response, but this is an inelastic response here. So we have some yielding of the structure, and we're not returning to 0. The type of nonlinear behavior has an effect on how big that inelastic response is. Often we idealize things as elastic plastic, but really many of our systems have a significant post-yield stiffness. So it's elastic and then elastic at a lower slope. Some things, however, degrade, and here's a post-elastic stiffness, and some things are very brittle and really can't go significantly beyond their elastic limit. So each of these has different characteristics that perhaps reflect on the, amongst other things, the degree of energy that's absorbed, and certainly on the amount of inelastic drift that the system can take before it loses its lateral stability. As we allow the structure to go beyond its elastic limit, you can imagine that effectively our stiffness is reduced. So if we yield the structure, we are perhaps not increasing the resistance proportionally with the drift, and so effectively our stiffness is smaller. And if you plug in a smaller stiffness into the period equation, you get a longer period. So a longer period structure generally has less acceleration. So it may get us out of this constant acceleration region into a period-dependent acceleration region, and thus reduce the forces in the structure through yielding. You should be aware, though, that increasing period increases the displacement. So as we make the structure softer, obviously it has less resistance, and it tends to go out to larger displacement. So accepting inelastic behavior means reducing forces but increasing drift. So we can use an elastic response spectrum to establish forces that correspond to elastic behavior. If we design for those forces without any reduction, we will have a very robust structure, but extremely high forces. So it may be a perfectly reasonable approach for a nuclear power facility to not accept seismic damage. But it's not a very economical solution for designing every single house in the U.S. not to have any damage under seismic loads. Using our money to make houses that way will not keep more people housed. Instead, we allow for some inelastic response. Accelerations are therefore reduced, and those accelerations correspond either to a reduction using the elastic spectrum, or what's seldom done is to create an inelastic response spectrum and use that directly. In either case, by allowing a reduction in force, we're implicitly allowing for structural damage. So we're reducing our forces beyond what the elastic spectrum tells us, and that tells us that we need to plan on inelastic response. All right. So here is a force displacement graph. So we're showing we're showing elastic behavior and then perfectly plastic behavior. The force is released, and we have an elastic rebound with some permanent displacement. Their force times displacement, those units are energy units. And the area under this curve is energy that is absorbed. So if you think about just the elastic region, if something remains elastic and you hit it with a lateral force, you build up strain energy, and say it's a moment frame, and beams and columns as you put them in flexure. The force is removed and there's a rebound, and that elastic energy is returned to the system, and perhaps it vibrates back and forth until all of that energy is absorbed in the small level of damping that we have in the frame. So that's the elastic response. If instead we take the structure beyond the elastic limit, perhaps out to a large inelastic drift, and then let go, there's a portion of that force that's still elastic energy in the beams and columns and is returned to that system. But there's a plastic rotation that we're putting, say, those beam to column connections through, and that's not returning back on its own. And the more the inelastic rotation occurs in those elements, the more energy is dissipated. So if you've had the experience of being in a testing lab when some sort of seismic testing like this has been going on, you might observe that the beams and columns do heat up a little bit as energy is dissipated through yielding. And this behavior may affect a little bit the ductility in general. The warmer something is, the warmer steel is, the more ductile it is. And that's an interesting phenomenon directly related to the energy dissipated through inelastic drift. Okay, so as I said, we could construct a spectrum. We do construct spectra using elastic oscillators. We could also construct a spectrum using those elastic oscillators with a high level of damping, and that will have less response. So for the same period of oscillator, if you increase the damping, you decrease the response. And so you can graph a curve for a highly damped response spectrum. As we allow different elements to yield in our response spectrum, effectively we are moving from the lightly damped spectrum to the more heavily damped spectrum. So as we increase damping, we're reducing response. As I said earlier, also as we allow the structural system to yield, effectively we are reducing the period. So the period gets longer, and regardless of which spectrum we are on, we go from one period to the other period. In this period-dependent region, the response is going to get lower. Typically, we look at this acceleration spectrum, and the acceleration response reduces. So as we allow the structure to yield and soften, we move down that period-dependent region and reduce the acceleration accordingly. So the elastic structure was up here. It was lightly damped and was relatively stiff compared to where it ends up. As it yields, the damping increases and the period elongates, and our response is actually here. So we may be designing, looking at a force up here, but implicitly by accepting structural damage, we're going to a longer period and correspondingly longer drift. and developing lower forces within that structure. And that reduction, both the hysteretic energy absorption and the period elongation, both of those things are implicit in the use of an R factor to reduce our forces. So these reductions depend on the system characteristic, such as ductility of the system, which is to say its capacity to tolerate large displacements. So you wouldn't use a high R factor for something that couldn't go out to large displacements. Also the post-elastic stiffness. So if you have a lot of stiffness beyond first yield, maybe your first yield doesn't have to be all that strong compared to your full strength of the system. The damping that the system has generally shows up in analyses of the system as reduced response. And so systems with a lot of damping tend to have higher R factors. Also, systems that degrade tend to have increased response and generally have lower R factors. So in many respects, the R factor is an overall estimate of the ductility and quality of the system and how much we can rely on that system for integrity of our lateral system at large displacements. And using an R factor with an elastic spectrum approximates what happens if we did a response spectrum using inelastic oscillators. Let's talk about system ductility. So if we look at force versus displacement, if we design for an R factor of 1, it's a very large force. It's the complete elastic design. And so we resist everything through elastic strains in our frame. And when the loading stops, our frame relaxes, and presumably we have no inelastic demand, no structural damage. You can design for a lower force, take a lot of it or less of it in elastic response, but we still need to go out to large drifts. And so the remainder of that ends up being through inelastic drift. So designing for an R factor, say reducing by a ductility factor of 4 our force level, means that we have a lot of inelastic drift to go through. So there are two components to the R factor. One is ductility and the other is overstrength. We're focusing on ductility. So a ductility factor of 4 might correspond to something like an R of 8, let's say, R of 6 to R of 8. And that means that there's a fair amount of inelastic displacement the frame has to go through. And that R factor reflects the ductility that can be tolerated. So let's talk a little bit about ductility and how it helps us reduce our forces. So what do we mean by ductility? Well, we typically mean one of two things. We mean a comparison of our yield displacement to either the ductility capacity of an element or frame or the ductility demand. So it really depends on context. So it's the ratio of one of these two, ductility capacity or ductility demand, to our yield displacement. So depending on context, we saw this photograph before, and we can say that that building experienced a lot of ductility demand, and probably a ductility demand beyond its ductility capacity, right? It doesn't look like it's maintained its integrity. So that is looking at ductility as a demand. And here on the right, we're looking perhaps at a test run in a laboratory And we can say that specimen, whatever it was, a moment frame beam, a buckling restrained brace, it exhibited a lot of ductility, meaning that it has a lot of ability to deform. And we can use it in a high R factor system and rely on its ductility to provide for the system integrity at large displacements. So it's very good to have ductility. It's very good to have our cars designed for crumple zones to protect the occupants for a head-on collision. But it's not so good to use it, right? So if you have an owner that's interested in protecting assets and minimizing downtime, you might have to have a conversation about what the building code promises and what the building code does not guarantee. So a lot of facilities, a lot of owners have expectations beyond the code. Hospitals expect to have continued operation. Many manufacturers have not only the interest in their building as an asset, but rely on the money generated by keeping that building functioning. And so the cost of repair is really heavily outweighed by the cost of having a facility taken offline. So when we're designing for structural ductility, we are designing for structural damage. And it's an economical way to design in terms of the cost of the structure, the amount of construction dollars spent reconstructing buildings that are damaged in an earthquake, as opposed to constructing everything not to be damaged in an earthquake. But it may not be the right answer for every owner. All right, so we have our design base here is some coefficient times the weight of the structure. And that coefficient can be the elastic coefficient that we get from the spectrum reduced considering the ductility. So we can design for a lower lateral strength depending on the ductility of the structure. And that factor is going to tell us what our reduction is. So we call that factor R sub mu, and that's a big component of the R factor reflecting the ductility. So how do we get a good R factor system? Later on today, later on in this course, we're going to be designing a steel moment frame and a steel buckling restrained braced frame. Both of these systems have been given the highest R factor there is, an R of 8. How do they get that R factor? Well, we'll talk about steel behavior, material ductility, section ductility, member ductility, all building up to system ductility. So first of all, talk a little bit about steel behavior. What is yield? So here's an idealized stress strain curve overlaid with photographs of a tensile coupon, yielding and then necking and then rupturing. This has very good elongation capacity. You can see the stress builds up in an elastic region, and then there's a pretty long inelastic. We'll call it a plateau. It's got a bit of a hump to it. And that goes out to larger and larger strains, but not building up a lot of extra force. If we have an element that only can take stress up to an elastic limit, and we put some stress on it, there are always some sort of discontinuities and non-uniform stress distributions. If we're limited by the peak stress, then this is as much force as we can put into the element. And only part of it is at peak stress. A lot of the section is at stress much lower than peak stress. Now, if we have a ductile material, like that steel that I just showed you, we have peak strain in the same location, and that's way out here. But our strain may be lower at the edge of this material, but our stress isn't necessarily proportionally lower. Our stress can be fairly high there too. And so when you integrate that stress across this portion of the section, you get a higher force. So we're utilizing this material more because it's more ductile. So ductility isn't just displacement capacity, it builds up into extra strength as well. All right, so ductile materials and non-ductile materials, right? If you integrate this stress strain curve, you can get a fully developed section with a ductile material and only partially developed with a non-ductile material. Now, often we have strain not just in the longitudinal direction of an element, but we might have strains that build up transverse to that principal strain. So if you recall von Mises' interaction formula, there's an interaction between principal stresses in the orthogonal directions on shear as well, and you form this yield cylinder. Oops, misspelled there. Yield cylinder, where if you have similar stresses in the three in these three directions, you can prevent that element from yielding. There's the von Mises ellipse in plane, but in 3 dimensions, it's a cylinder. And so what does that mean? If we're preventing it from yielding, we're preventing it from exhibiting that ductility. So let's look at that coupon again, and instead of just a smooth coupon, we've notched it. And that notch has permits the coupon, or makes the coupon, build up some transverse stresses. So it's similar to triaxial loading. As we stress it in its longitudinal direction, it tries to reduce its cross section due to Poisson's effect. But the higher stressed area in the middle can't reduce because it's restrained by the lower stressed area immediately above and below it. So these transverse stresses build up, and we end up with restraint and the inability to yield. So the stress strain curve for this element, instead of having this prolonged yield plateau, essentially keeps going up until it reaches the rupture stress. So there is an interaction in rupture, but it's not the yielding sort of behavior that you have in yield. So when you have conditions with high restraint, you perhaps, even though you're using a ductile material, you may not see the ductility in that element. So here, minimal restraint is the coupon, and as we pull on that coupon, we get the maximum elongation that we can get out of that material. And indeed, that's how we measure elongation for the material. We can introduce some restraint. This is a plate element. There's some through thickness restraint for thicker elements, but generally we taper it to try to minimize that through thickness. But we do have restraint in the width of the plate. So, for example, a welded column splice like this has a bit of restraint due to the fact that it's a plate element as compared to a coupon element. It's still about as good as you get in structural design. And then if you have restraint in 2 orthogonal directions, such as in this beam flange to column flange weld, it's a very thick column flange. It extends in both directions, and that's a highly restrained condition, and it's very tough to get much inelastic strain out of the steel material immediately here. So we'll see when we talk about moment frames that we simply don't want to ask for ductility from this element, we want to move that ductility demand away from it. Okay, so we want elongation capacity, we want predictable yield strength, we'll get into that a little bit later. We want to avoid brittle failure, low strain capacity. We're going to provide mild structural steel and, crucially, a length over which we can develop large strains. We're going to avoid work-hardened material, highly restrained conditions, through thickness loading, and notches. So that's our steel stress strain curve. Now we'll talk about sections. When we're expecting ductility out of the section, we want to yield the entire section in either tension or compression because earthquake loads are reversible. Generally, we want to avoid local buckling. We want to avoid tensile rupture. Here's the stress strain curve, and because I think I want to reverse it with reversing seismic loading, here it is again on the opposite side. If this is a beam, I'm putting through rotation, I build up strains and stresses, and I get to yielding. And at different points in that in the depth of the beam, I'm at different points along this yield plateau. But I'd like to be able to mobilize pretty much the entire section into the yield plateau. So I want to be able to go through fairly high strains in that flange and not be subject to rupture or premature local buckling. So this is a moment frame connection. I don't know that this local buckling was premature, but eventually the ductility was limited in this case by local buckling. Of course, many of these moment frame connections, the ductility will either be limited by local buckling or by flange rupture. Okay. So we want to provide for our sections of ductile material. We also want to provide, and this is crucial, highly compact sections that can develop full yield before local buckling. So we want to avoid slender sections, holes, and other reductions in the cross-section. And we want to configure our access holes to avoid local rupture. So compactness, the seismic provisions tell us to limit, how to limit our B over T ratios for tubes and for flanges, H over TW for web, and B over T for round sections. By using stockier sections, we get better behavior. This is a moment versus rotation graph. Here I'm showing it idealized for a slender element. We get up to a certain moment and then we get local buckling. Non-compact, we don't get, we get into yield but not full yield of that section. And then there's local buckling. Compact sections get up to the full yield and go through a defined rotation before local buckling. And then we have what the seismic provisions require, seismically compact, even lower B over T ratio, so a stockier section there. And they go through significant inelastic rotation before they start to degrade. Now we use those sections in members. We want the member to exhibit ductility, so we want it to yield either in flexure or axial or shear. We don't want connection failure. Generally, we don't want member instability. So we'll use the ductile material, the ductile section. For moment frames, we provide lateral bracing to make sure we can get that flexural ductility and not lateral torsional buckling. And we make our connections stronger than our members. That's how we ensure ductility comes from the member. We avoid unstable conditions, weak connections, weak areas of members. So this is a graph from a test, a beam to column connection cycled back and forth. And you can see there's pretty ductile behavior in terms of moment versus rotation. So overall, something that looks not too dissimilar from the stress strain curve. This is a connection, I believe, without any lateral bracing near the connection, and there's a little bit of twisting of the beam. So generally, in our moment frame beams, we do provide lateral bracing at frequent intervals to make sure we can develop that full yield. We also pay attention to connections that could rupture before we get much ductility out of the element. And so we use often reinforcements at connections in order to ensure that the member can develop ductility, and we don't limit the ductility of the member by having rupture at the connection. For moment frame connections, so that's a braced frame connection, braced to gusset connection, slotted, and in the previous slides you see where that has often, on the left in the laboratory, on the right in an earthquake, that has often failed. It's been a weak point in that brace connection. And so here in this test, similar brace connection but with a reinforcing plate, and that drove the ductility into the bracing member. Here the moment frame beam is connected. It's reinforced with a cover plate to drive the yielding away from the face of the column, that highly restrained condition that I spoke about a little while ago. And this is with a pair of haunches, again, driving the yielding, as you can see, quite successfully away from the face of the column into the beam, maybe half a beam depth in from the face of the column. And it protects that highly restrained condition and allows yielding under essentially that plate-type condition of the beam flange. And this is a similar approach. This is a reduced beam section connection. So if you look at these beam flanges, you can see they've been cut away. So the connection hasn't been strengthened, but the proportioning has been changed such that the connection is stronger than the reduced beam, just a little bit in from it. So seismic design is often less about strength than about proportioning, making sure the structure is well proportioned to get yielding where yielding can occur, and to keep yielding away from where, or to keep inelastic demands from where there might be a non-ductile rupture type of failure. In order to do that proportioning, we have to understand the expected strength of our elements. Often we use a specified minimum yield strength that is quite a bit lower than what the coupon test will show. And that material overstrength is often significant. It can be 10% or as high as 60%. It varies material by material. And our building code, AISC 341, the seismic provision, defines what it is the engineer should consider. So there's a quantity here, FYE. That is the expected yield strength of the material, defined as a factor RY times FY. So our A992 material has a specified minimum of 50 KSI and an RY factor of 1.1. So the FY expected for that material is 55 KSI. That's not the upper bound. The upper bound as defined for that material is 65 KSI. But on average, you will do fine assuming that it yields at 55 KSI. So the idea is that this expected yield strength is more or less the true expected value. It's not the upper bound value. But use in our design equation still produces a reliable design because we're using resistance factors and so on. So the RY factors that we have in the code are appropriate for each material and have been selected based on the members that would be used out of that material. So only the relevant data has been considered. Also, our material tends to strain harden. For braces, typical braces, they may strain harden a little bit, but the strain tends to be reasonably well distributed. And so it's about 10%, and to keep our design methods fairly simple, we don't include that in the design of bracing connections. For other systems, say buckling restrained braced frames or eccentrically braced frames, it can be larger. So it might be 40%. And that's too much not to include, and so we do include those values in the design methods for those systems. And again, for moment frames, it's large enough to be considered, and so you'll find that in our design procedures as well. And each of these systems tells you how and how much to consider strain hardening. For system ductility, it's so we have ductile members now. We have strong connections. Now we want system ductility. It's desirable to have large roof displacements. It's in order to get these large roof displacement capacities, we want to distribute our ductility demands. If we concentrate our ductility demands, we will be severely limited in our overall drift. We want to maintain our lateral resistance at large drifts, and we want to be able to tolerate damage. So we want to avoid loss of lateral resistance, excessive member ductility demands, and instability. And generally, we want to design where it's just a matter of degree of ductility rather than being right on the edge of failure. So to get system ductility, we want ductile material, but that's not enough. We want ductile sections. That's not enough. Ductile members. That's not enough. We need sufficient strength, sufficient stiffness, and very important, we need to proportion our system to spread yielding. And then we want the members capable of providing that ductility, and hopefully with some post-yield hardening. We want to avoid weak zones in our structure. We want to avoid unproportioned overstrength, and we want to avoid structures with negative post-yield stiffness. So this is a force displacement graph from a study, a recent study. It's an eccentrically braced frame, and you can see that the roof displacement goes out quite far, and it looks maybe not exactly, but not too dissimilar from that ductile steel stress strain curve. So the idea is through proper selection of material, through proper selection of sections, design of members, and using of strong connections and proportioning of the frame, we get system ductility. So steel is ductile, yes, but that's not enough to give us a ductile system. So we avoid concentrated ductility, and this is a graph for a similar study where the ductility was concentrated. And we try to encourage distributed ductility that leads to much greater system ductility. And as I said, proportioning is very key. So in this diagram, I'm showing a 20 amp fuse on the left and a 30 amp fuse on the right. And 30 amps seems better than 20 amps, but you can't say that the system with the 30 amp fuse is better than the system with the 20 amp fuse. Fuses are all about proportioning to protect elements. So if we have a system that can only take 25 amps, the 20 amp fuse is well proportioned to protect that system, and the 30 amp fuse is useless. You might as well not use it at all. So seismic design is like that. We select the element, let's say it's a buckling restrained brace. It will protect the column from buckling. It will protect the beam from failure. It will yield when we expect it to yield, and we have proportioned the system so that the beam and column don't fail, but that we'll get the yielding in those braces. Okay, so we started with a ductile material. We selected ductile sections. Now we configured them in ductile members, made sure our connections were strong enough, and proportioned them into a ductile system. That's how we intend to get system ductility. We'll talk a little bit now about steel lateral systems, moment frames. We have conventional moment frames, truss moment frames. We have braced frames and shear walls, and composite moment frames, and composite braced frames and shear walls. We're not going to talk about all of the systems, just the major steel ones, and we'll steer clear of the composite ones for the moment. Moment frames, we have special moment frames that are detailed and proportioned for large inelastic drift. They're given a high R factor, so the required strength is relatively low. We have intermediate moment frames. These are detailed in proportion for less inelastic drift. We'll call it moderate. And they're given a correspondingly more moderate R factor, 4.5. So the higher the R factor, the lower the design force. So we're designing these for higher strength. And then we have ordinary moment frames. They are detailed in proportion for relatively small inelastic drift. And they're given an R factor of 3.5. So they're designed for quite a bit more than the other systems. So in moment frames, we're encouraging flexural hinging in the beams, and we're trying to avoid flexural hinging at the columns, recognizing that you can't form a complete mechanism. You can't get out to large inelastic drift without something happening at the column base. So this is the sort of mechanism that we anticipate that we would like to encourage. Beams being weaker than columns, columns being stronger than beams, and then perhaps you get some rotation at the base. So each of these red dots would indicate some inelastic flexural behavior. And those beam plastic hinges are essentially the fuse of the system. So that defines the maximum force, say the maximum flexural force that can be delivered to the column. It also helps us capture the maximum shear that the beam will see and a bunch of other things. So that's the fuse of the system. If we proportion it correctly, we avoid a situation like this where we're forming plastic hinges top and bottom of that first floor column. We don't like the plastic hinges in the column, and this also is very concentrated ductility that could lead to very little inelastic drift capacity. We also want to avoid connection failure. We get a lot of ductility out of the beam rotation, not a lot out of failure of welds and bolts. And in general, we try to preclude excessive panel zone yielding, as we'll discuss in the moment frame sections. Braced frames, we have the buckling restrained braced frame, large inelastic drift, R of 8. Special concentrically braced frame, less inelastic drift, R of 6. Ordinary concentrically braced frame, very little in the way of detailing requirements because we don't expect large drift demands, and it gets an R of 3.25, the lowest of any of the braced frame systems. We want to proportion these to encourage yielding of the braces, which act as the fuses. It could be buckling of the braces for the special concentrically braced frame. And we want to avoid this sort of story mechanism. Certainly we want to avoid column buckling or connection failure. Buckling restrained braced frames are very similar. We'll talk about how those braces behave. The only difference is the buckling restrained braced frames, or the buckling restrained braces, don't buckle. They yield in tension or compression. And again, we proportion to avoid the story mechanism, to avoid column buckling or connection failure. Eccentrically braced frames, excuse me. Eccentrically braced frames go to large inelastic drift. They get an R of 8. Steel plate shear walls, also a very ductile system. With the eccentrically braced frames, the link is where we expect all the inelastic action. It could be flexural or shear yielding of the link. That's the fuse. And that protects the columns, the braces, and the connections. Steel plate shear walls, it's yielding of the web plate in tension, combined with a sort of backup frame, yielding in flexure. That's the fuse that defines the maximum force that, say, the columns will resist. We want to proportion it to avoid a story mechanism. We want to avoid column buckling, and we want to avoid beam buckling as well. And, of course, connection failure. So, to summarize, we need to perform seismic design to provide structural safety to protect the public and our clients. Our building dynamic characteristics affect the response. System ductility permits us to design for reduced forces. And steel provides excellent ductility if we properly design it, following the principles that I outlined, using ductile material, ductile sections, ductile members, and proportioning the system. And each of our steel lateral systems has a set of strength, detailing, and proportioning requirements that help us get to a ductile system. So with that, we're at the end of session 1. Next week we have seismic design of moment frames. And I've selected a few books that I have drawn on in putting together these principles, in addition to the resources we had at the front end: Farzad Naeem's Seismic Design Handbook, Fundamental Concepts of Earthquake Engineering by Villaverde, and Anil Chopra's text on structural dynamics. I think he also has a textbook out now that's a little bit more modern than the one on my shelf. So with that, we arrive at the end of the session.
Okay, thank you, Raphael. And we do have some questions from the audience. But first, we'd like to ask the audience a few questions. We have a couple polling questions. See if everyone was paying attention tonight. Okay, so our first question is the following. Increasing the structural stiffness will A, decrease the period, B, increase the period, or C, does not affect the period. You can submit your answer by clicking on the radio button next to the answer you believe is correct. Once again, increasing the structural stiffness will A, decrease the period, B, increase the period, or C, does not affect the period. Give everyone a couple more seconds. Go ahead and submit your answer now if you can. Okay, I'm going to go ahead and close the poll then, Raphael. And over 90% said A, decreases the period. What do you think? Raphael, you still there?
Sorry, I went on mute.
That's okay. Yeah, everyone's in suspense. So what's the correct answer?
I'll go with the audience on this one.
All right. A, increasing the structural stiffness decreases the period. All right. All right, let's check one more polling question, and then we'll get to the Q&A. Our next question is this: true or false? Systems that allow for higher inelastic deformation can be designed for lower design loads. True or false? Systems that allow for higher inelastic deformation can be designed for lower design loads. All right, things are slowing down here. All right. And overwhelmingly, people thought that was true. What do you think?
Yeah. So if we have a system that can go out to large inelastic rotation, we can design it for a relatively low force and rely on a great degree of displacement beyond the elastic range.
Okay, great. All right. For our first question, I'm going to go to slide 36. And that is 35. Okay.
Right, yes.
Here's the first question. It was mentioned that we used to use a single ground motion record. The question is this: was the original ground motion data the El Centro record? And when did such a practice change to consider numerous ground motion records?
So that's an excellent question. Unfortunately, I don't have the answer. Well, I have the answer to the first one. Yes, El Centro was the only one used for many, many years. I am, I guess, young enough not to know when other ground motions were added to our suite of motions, and to create a more generalized response spectrum. Of course, now we have a lot more recordings than we had even 5 years ago. So unfortunately, I don't know when other recordings were added. But yes, it was El Centro, and many code provisions were tuned just to responses from that El Centro record.
Okay. I'm going to go to, I think slide 80 would be appropriate for this next question. Can you clarify what is the definition of hysteretic damping, and can you give examples of systems that illustrate hysteretic damping and cyclic degradation?
Okay. So yeah, let's start with the definition of hysteretic damping. So as I explained, let's see if we take a, this is a good slide, but maybe if we go to 44 briefly. This is a reminder. So here we have a structure that we've taken past the elastic region through some inelastic drift and then let it relax. And there is an area under the curve, and that area is actually in units of energy, and it does represent hysteretic energy. So that is energy that is not returned to the system, but goes into, say, heating the steel or other or somewhere else that doesn't result in more acceleration or strain energy in the structure. So if we return now to the slide you selected, which is a good one, which is an actual laboratory test. This is a beam to column connection. If you cycle this cycle the beam to column connection as is being shown in the little diagram in the upper left, pushing it up and pushing it down. You know, if you break for lunch, look at all the way at the lower left. You stop loading it and you let it relax. It goes out to some. It comes back a little bit from its maximum displacement. That area under the graph is hysteretic energy that's been dissipated, that has actually gone into heat that you can feel in the steel. Each of these cycles has an area to it, and that is energy that is dissipated. That is earthquake energy that is absorbed by the system and not returned like a spring returning the energy to vibrate the system more. So that's so here. This is a moment frame. Essentially, this is force displacement, but it could be moment. You could translate that into moment rotation graph that shows good hysteretic energy dissipation. And you can see a similar graph for testing of a buckling restrained brace. We'll see that in a few sessions. There are similar graphs for this for eccentrically braced frames. Each of these systems has a lot of has a force displacement or moment rotation graph that looks kind of like this. It's very reminiscent of the yield plateau. It's a bit more rounded because here not all of the section is yielding at the same time. It has to go through a fair amount of rotation from initial yielding at the extreme fiber to developing of the pretty complete plastic hinge. Nevertheless, it does look like the steel stress strain curve, just a bit more rounded. Now other systems, and I think we'll show this when we talk about braced frames, buckling of a brace, on the compression side, it reaches a peak force, and at just a little bit more displacement beyond that, it tends to reduce its force, sometimes dramatically. If it's a very slender brace or an intermediate brace, it can lose a lot of strength in just a little bit of drift. If it's a very stocky brace, it tends to squash or buckle in a more controlled fashion. But a slender brace or an intermediate brace is going to buckle and degrade almost immediately in that first cycle. And then if you go to subsequent cycles, it never gets up to that maximum force again because it never becomes fully straightened. So I like this question, and we'll come back to it in session 3 when we're talking about braced frames, and we'll talk about degradation of the brace as it goes through cyclic buckling.
Okay. All right, I'm going to jump to slide 33, and I think the general question is, can you expand on this slide here and on the period-dependent responses of the various models?
Okay, so so let's look at this slide, and let's also look at 36. So if you have a ground motion, in slide 33 it was a simple sine wave, and in 33 this is literally what I did. I used a MathCAD sheet with a sine wave input and just a single degree of freedom oscillator. In this case, it's pure resonance that the oscillator that has a very short period on the left is not very close to the period of the ground motion. But then as we get towards the middle, we're very close to the period of the ground motion. And so there's a resonance between the input motion and the period of the oscillator. And then as we move further right to the other oscillators that are longer period, we get out of that resonance range and the response is more controlled. Now when we go to an earthquake ground motion, mathematically we could deconstruct that complicated motion into frequency content at different, essentially as an accumulation of or as an assembly of many different sine waves of different periods and different amplitudes. Or we could interrogate the ground motion by running essentially a bunch of analyses of these little oscillators of different periods and seeing what their response is. And that gives us this response spectrum. So let's say we do it not just for one ground motion, but we do it for 100 ground motions, and average them, somehow come up with a generalized response spectrum. Then we design our building using that response spectrum, and if our building is a short period building, maybe it gets designed for a higher force, and if our building's a longer period structure, it gets designed for a lower force. And then we have an earthquake, and if that earthquake is generally representative of the characteristics of the earthquakes we used to create this response spectrum, then maybe our response will be similar to what we predicted or what we used, what we got from the response spectrum. So after an earthquake, it's always very interesting to see what the earthquake response spectrum looks like for that particular earthquake. And sometimes they're complicated, and sometimes they have a spike or an unexpected very high portion, say at 2 seconds or 3 seconds. And maybe buildings of a certain height tended to suffer, and it just happened to be those buildings that had that natural period that got hit harder than one might expect. So hopefully that addresses the question. The response spectrum comes from data, earthquake data that's been recorded, and we hope represents earthquake demands that haven't occurred yet.
Okay, here's a question, and maybe this we'll need to wait for one of the later sessions, but why is there a limitation on different types of moment frames with respect to seismic design categories?
That's a very good question. So you would think if if the R of 3 moment frame works for peak ground acceleration of 0.1, it would work for 0.2, 0.3. The real issue is that there's quite a bit of uncertainty in terms of the acceleration levels that might occur due to seismic design. And generally, the profession and the code writers feel a bit more comfortable with systems that have large displacement capacity, that if the earthquake is 20, 30, 40% larger, that these systems will perhaps see a little bit more damage or a bit more damage, but will still, in principle, behave as designed. That is to say, going out to large inelastic drift and maintaining their integrity. Whereas low ductility systems, we think if the earthquake force is bumped up by a similar factor, perhaps because they're not well proportioned, it goes from a sort of moderate response immediately to an extreme response as connections fracture and the entire lateral system loses strength.
Okay, I think we have time for a couple more questions here. I'm going to go to slide 89. When it comes to system ductility, you show on the left-hand column you need to provide a system proportion to spread yielding. Is it possible to provide an example of when you would have an unproportioned system that may not perform well?
Yes. So this occurred. I'll go to this slide. This was an unfortunate byproduct of some of the attention that we gave to moment frames after the Northridge earthquake. There was, in the years immediately after that, there was a heavy reliance on tested connections. We'll talk about this in a couple of weeks, or I guess next week. We discovered after that earthquake that some of the design techniques, some of the design and construction techniques that we had for special moment frames did not result in the ductile behavior at the beam to column connection that we had anticipated. And so in a couple of years immediately after that, many jurisdictions required testing and testing of similar sizes to validate a design. So if you had a 4, 6, or 7-story office building, and perhaps your design was finished and your owner was ready to build it, the owner now had to face a testing requirement, and the owner maybe wasn't interested in testing 7, 12, or 15 different beam to column combinations. And so instead the owner said, well, let's just make them all the same W36 beam, and we'll test that, and if that works, we'll use it everywhere. And of course, if you have a 4, 6, 10-story building, and all the beams have the same strength, the demands on the beams lower in the building will be much larger than upper levels. And so that does tend to produce a very poorly proportioned structure that is highly likely to have damage concentrated in the first couple of stories and to have no inelastic demands in the upper stories of the building. I've seen it also with braced frames, but perhaps not for any good reason.
Okay. All right. Well, we are officially out of time. Well, that does it for tonight. My thanks to Rafael Sibeli for tonight's presentation, and thank you all for joining.